Today, we are going to tackle one of the biggest, most persistent puzzles in all of astrophysics. It's a real head-scratcher about our very own sun, and we're going to see how an invisible wave, dreamt up decades ago, might just be the key that unlocks the whole thing. All right, let's get right into it.
So here it is. This is the big mystery. You know how when you stand by a campfire, the farther you back away, the colder it gets? I mean, that's just common sense, right? Basic physics. But the sun, it does the exact opposite. Its surface is incredibly hot, yeah, but its outer atmosphere, the corona, is hundreds of times hotter. And the question that's baffled scientists for years is, why?
And the numbers here are just wild. We're talking about a surface that's simmering at around 6,000 Kelvin. But the corona, way out in the sun's atmosphere, is blazing at over 1,000,000 Kelvin. It just makes no sense. How on earth can energy be flowing away from the sun, but somehow superheating the atmosphere that's farther out?
To even begin to crack this problem, we have to hop in a time machine and go all the way back to 1942. A Swedish scientist named Alfvén came up with this pretty radical idea. He imagined a totally new kind of wave, one that could ferry enormous amounts of energy right through the sun's plasma.
And this right here, this is the key phrase from his original paper. He figured out that inside a plasma, which is just a super, super hot gas of charged particles, the stuff the sun is made of, the magnetic fields and the fluid motion are basically locked together. They're dance partners. If you move one, you move the other. And that creates this unique electromagnetic hydrodynamic wave. So what exactly is an Alfvén wave? Well, in the simplest terms, it's a wave that zips through plasma. And the definition here gives us the two crucial ingredients. First, you've got these magnetic field lines that act like they're pulled tight. They have tension. And second, you've got the actual stuff of the plasma, the ions, which gives it weight, or inertia. So you have tension and you have mass. Now that combination should start to sound a little familiar. And get this idea wasn't just some neat little theory. It was so revolutionary, so absolutely fundamental to our understanding of the universe, that almost 30 years later, Hannes Alfvén won the Nobel Prize in Physics. I mean, he basically created an entire new field of study. Okay, the technical definition is cool and all, but to really get a feel for how this works, we need a good analogy. And honestly, the best way to do that is to think of the sun's magnetic field as a giant, cosmic guitar. No, seriously, a guitar string. It sounds simple, but the physics behind a vibrating guitar string and an Alfvén wave are shockingly similar. It's just, scaled up to the size of a star. So let's break this down. 1. Picture those magnetic field lines stretching out from the sun. They're like the strings pulled tight. 2. The plasma itself, all those particles, they cling to the field lines. That's what gives the strings their mass. 3. You've got the churning, boiling surface of the sun. It's constantly in motion, and that turbulence literally plucks those magnetic strings. And 4. Boom. The energy from that pluck travels down the line as a wave. That right there is your Alfvén wave. Okay, so the theory is brilliant, right? It's elegant, but is it real? Proving it actually exists was a whole other challenge. In fact, the hunt for Alfvén's wave took scientists on an incredible 80-year journey, from the lab bench all the way to deep space. And what a journey it was! At first, things moved surprisingly fast. By 1949, they'd actually created one in a lab. Then came the Nobel Prize, cementing the theory's importance. But spotting one out in the wild, out in space, that was way harder. It took until 2007 to get the first direct look at them in the sun's corona. And now, very recently, we've gotten the final confirmation. Yep, these waves are definitely heating up the solar wind. Now, that 2007 discovery was huge, but it came with a big but. The waves they saw were, well, they were kind of wimpy. They didn't seem to pack enough punch to explain that million-degree temperature mystery. But then 2011 rolls around, and with better instruments, scientists found waves with speeds of 20 kilometers per second, not half a kilometer. That's a massive difference in energy, way more than enough to do the job. Turns out, the powerful waves were there all along. We just needed better eyes to see them. So, case closed on the sun's crazy hot atmosphere, right? Well, not so fast. Because this is where the story gets even bigger. Alfvén waves aren't just a solar thing. They are a fundamental process in the universe. They're pretty much everywhere. One of their biggest jobs has to do with something that affects us right here on Earth, the solar wind. That's the constant stream of particles flowing off the sun. And in a very real way, These waves set the rules of the road for that wind. They act like a cosmic speed limit.
It all comes down to something called the Alfvén Mach number. Think of it like swimming in a river. When the wind is subalfvenic, the current is slow. Information carried by the waves can actually travel upstream against the flow. But once the wind speeds up and goes superalfvenic, it's like the river becomes a raging rapid. Everything gets swept downstream. That tipping point is absolutely critical for understanding how energy moves through our solar system.
So when you put it all together, the impact of these waves is just immense. They heat the sun's corona? Check. They accelerate the solar wind? Check. That means they're a key player in the space weather that can mess with our satellites. They even play a part in creating the beautiful auroras. And it's not just local. We see their effects in massive energy jets shooting out of distant black holes. It's truly mind-boggling. You know, we started with a simple, almost paradoxical question about the sun's temperature. And the answer led us to this invisible cosmic wave that turns out to be one of the fundamental forces of the universe. It really makes you wonder, doesn't it? What other enormous cosmic secrets are just out there, hiding in plain sight, waiting for us to finally figure out how to look for them?